Hi guys, in this video we're going to take a quick look at the chemistry behind penicillins. Obviously penicillins are used to treat a variety of bacterial infections. They do so by inhibiting bacterial cell wall synthesis, particularly the cross-linking. When we're looking at the cross-linking, we're looking at these things that I'm highlighting here. So basically penicillins stop this cross-linking occurring. So it says there, pentaglycine link inhibited by penicillin. Without these links, the bacteria will lose structural integrity and they will in fact die because penicillins are in fact bactericidal rather than bacteriostatic. That means they will actually kill bacteria rather than just stopping them grow. So let's just have a quick look at the bacterial cell wall structure. You can see we've got these NAM and NAG sugar units, and it shows you there here what the NAG and NAM are. NAG is when this R group is a hydrogen, NAM when this R group is this sort of carboxylic acid side chain. These NAM and NAG are linked together by a glycosidic link, just like you'd get when two glucose molecules join. So you get the OH from one of the sugar units and the H from the other. That then is lost as water, so minus H2O, and you get this new oxygen carbon bond formed. Again, same thing would happen on the neighbouring one. Again, OH there be lost, and you'd get a new carbon oxygen bond formed between the next sugar unit. We can see as well that we've got this sort of peptide here, and in reality what the NAM binds to, it binds to a pentapeptide with the following amino acids. And they're linked by the NH2 of this alanine. So what we've got here is we've got this alanine here, and this alanine has got an NH2 group, and what happens is that combines with the carboxylate group. So again, you get a condensation reaction, minus H2O, and you form a new nitrogen carbon bond, which is basically this bond here, which is basically that link. Yeah. So the link between the L-ALA and the NAM is due to the carboxylic acid combining with this amine to form an amide. It does say as well we've got this pentaglycine. So on this lysine group, this here is a pentaglycine, and what we've got there is 5 then glycines. Oops. I'll just copy that. So we've got glycine, so that's 3, 4, 5. So we've got these 5 glycines. So again, what's happening there is the lysine. You've got an N, H there, and that combines with the C, OH from glycine, and again it's another condensation reaction, and that there forms this another peptide link between the N and the C, which is this link here, okay, which would again be another condensation reaction. So penicillins then inhibit the cross-linking. We haven't really spoken much about what this cross-link is and how this is formed, but we'll do that on the next slide. Penicillins act as something called irreversible competitive inhibitors. We need to kind of unpick what that means. Competitive then implies that the structure of penicillin here resembles that of the normal substrate for the enzyme. Irreversible means that it's going to form a covalent interaction with the enzyme rather than weak sort of hydrogen bonds or van der Waals interactions. It will form actually a covalent bond in addition to these other interactions. That means then it must mimic the natural substrate. The natural substrate it's kind of mimicking is actually this part here, this ala part, or sometimes called the D-ala part. And we may be thinking, well, does it? How does it resemble it? Well, if I copy this structure down, so I'll just copy it rather than write it out again, then I can modify this very slightly, and actually by doing so we will actually get the structure of D-ala. We remove one of these CH3s, and we do need to remove this sulfur, and we're going to remove this bond here. Because we remove this bond here, we need to put hydrogen there. And that actually is the structure of the D-ala. Okay? So again, try that out. Try writing that out if you don't believe me. And this here, if I superimpose this onto the structure of penicillin, we can see that there is quite a close match. So you can see why it is a competitive inhibitor. They will form similar kind of binding interactions. So it's inhibiting an enzyme called DD transpeptidase. So that's the enzyme which penicillin is inhibiting. So let's have a look at the cross-linking stage. You can see here we've got a very nice diagram which shows you how bacteria form these cross-links. And I've drawn this D-ala structure out. And this D-ala structure here is basically this structure there. And we can see that it's been attacked by an enzyme, and I've got the enzyme here. And we see that it's attacking this D-ala residue, this sort of fourth one. If you say it's 1, 2, 3, 4, the fourth amino acid. So let's show this. So what's actually happening is that the lone pair is attacking this carbonyl-carbon, and it causes that bond to break. So what we're going to look at is the consequences now of these curly arrows. So this lone pair here is used to form a new carbon-carbon bond. So let's rub that out and actually put down the consequence of that arrow is this bond being formed. Because the oxygen has used its lone pair to form this new carbon-carbon bond, it now needs a positive charge, and I'm just going to draw this bond between the O and the H. The result of this curly arrow is that this bond is broken, and the pair of electrons that were in that bond are now lone pair on the oxygen. So that's the consequence of those arrows. So basically, it's showing you us what's happening in this curly arrow here. What happens next is that this double bond then is reformed, and now this carbon-nitrogen bond breaks, and this enzyme, oxygen, the positive charge in the oxygen is neutralised. And this here is in effect kicking out this alanine. So what's going to happen is that N is going to gain that hydrogen and is going to be lost. So let's show the consequence of these arrows. So the lone pair is being used to reform this double bond, and in the consequence the negative charge is neutralised. This bond has now broken, and the pair of electrons that were in this bond here are now being used to form a new bond between the N and the H there. So that curly arrow can go. This hydrogen now actually would be if I was going to draw it, would be now here. And again, because the pair of electrons have gone back to the oxygen, it loses this positive charge. So this here now is the alanine, which has been kicked off, which is basically this alanine here. So we kick this alanine out, and I'm going to get rid of that alanine. So this structure that we've got here is basically this structure that we've got here with the O enzyme. Now, this structure here now is going to be represented by this structure here. This is from the sort of five glycines together. So I'm going to move this a little bit closer. So what we've got now is this here is basically this here. And what's going to happen, it shows you there that the glycine is attacking this alanine residue, which is what we've got here. So let's show this by drawing a curly arrow. So that, in effect, this curly arrow here is analogous to this curly arrow here. So what's the result of this curly arrow? So we form this new nitrogen-carbon bond, and this double bond breaks. So let's show this. So lone pair there has been used, and we're going to form this new carbon-nitrogen bond. In the process, this nitrogen is going to gain a positive charge. And let's just draw these hydrogens out with bonds. And this double bond is now broken. So we need a negative charge and a lone pair. What happens next is this double bond reforms. This bond is now going to break. And the lone pair that's on here is going to get its hydrogen back off this hydrogen here. Now, the result of this is that the enzyme is going to be regenerated and we form this new cross link. So let's just show the consequence of this. This lone pair reforms, let's do it in black, forms a double bond. This bond has broken to regenerate the enzyme, and this curly arrow shows a new, this lone pair here used to form this covalent bond. So what we've got then is this OH, and we can see hopefully now that this enzyme has been regenerated. This will get its, as I said, get its lone pair of electrons back, and we form this cross link. This is the cross link that we formed, and this here is basically this here. So that basically shows you in detail how, sort of terms of mechanistically, how the bacteria synthesizes the cross link or forms the cross link. Now, how does penicillin stop this? So let's just copy penicillin. What happens here is when the enzyme attacks, again, it's going to attack, thinking this is very similar to the diala residue. And again, when you get any sort of reaction of a nucleophile with a carbonyl-carbon, you always break this carbon-oxygen double bond. The consequence of these arrows is that we're going to form a new oxygen-carbon bond. So let's just draw that. Again, this oxygen will need a positive charge, and we've broken this double bond here. So now this is now a single bond, and we need a negative charge and a lone pair. So that's what we've shown in the first step. Next step, double bond is reformed, and now we're going to break this carbon-nitrogen bond here. So I'm just going to show this bond in full. So what's going to happen now is that this bond is going to break and form a new bond with this hydrogen. And again, this bond is going to break. So in effect, the pair of electrons that were in this bond are now being used to form this new NH bond. This bond's broken, and this oxygen is going to get its lone pair back from this bond. So the consequence of this is that the double bond is reformed. This bond now has been broke. Let's draw this out again. So we've got now an NH there. This H has gone to the nitrogen, and again, the oxygen's positive charge has been neutralised. And that there forms this kind of stable enzyme penicillin sort of complex. Now this glycine here that wants to come and attack is blocked. It cannot actually attack. And that means it's irreversibly inhibiting the cell wall synthesis. Okay? So this now is just going to keep the enzyme immobilised. And again, it's an irreversible inhibitor because you've got this covalent bond between the enzyme and the drug. Okay, in the next video, we'll look at why penicillins are more reactive and different types of penicillins, how they're made, and we'll also look at how bacteria become resistant to penicillin. But that's for the next video.